Welcome to Science on Saturday. I'm Dr. Joanna Albala. I'm the Science Education Program Manager at Lawrence Livermore National Laboratory, and I'm so excited for this year's Science on Saturday theme, Up in the Air. The talks this month explore the innovative work at the lab with aerial and space-based equipment. So, without further ado, let's welcome our presenters today. Megan Eckhart received a BA in Physics and a BA in Astrophysics from the University of California, Berkeley, and a PhD in Physics from Caltech. Megan serves, woohoo! Megan serves as the director of the Lab's Space Science Institute, an organization that covers the astronomy and planetary science efforts at the lab. Joining her today is Natalie Hell, who received a BS, an MS, and a PhD in physics from the Friedrich Alexander Universität on Largen in Nuremberg, Germany. She's currently a staff scientist in the Astrophysics and Advanced Diagnostics group. And joining them today is Stan Hatomi, who received a BS in biology from the University of California, Berkeley, and a master's in athletic administration from St. Mary's College. He retired in 2020 after 31 years as a teacher, principal, and administrator in the San Ramon Valley Unified School District, and serves as a faculty scholar at the Lawrence Livermore National Lab in the Science Education Program. Let's give it up for Stan. So, the title of their talk today is Space Telescopes, Observing the X-ray Universe. Now, let's get started. Woohoo!
All right. Welcome, everyone. So before we dive into this very interesting topic, I'll introduce myself, and Natalie will introduce herself. The clicker.
It's not working. Yeah, no.
All right. So my name is Megan Eckhart. I was born in Australia. Probably can't tell from my accent, though. Moved back here and grew up locally. And I've always been drawn to science and math, but also spent a lot of time when I was your age playing soccer, swimming, learning to play the violin. And it was really in college that I decided to pursue astronomy and physics, and have been doing that ever since. After school, I moved from California to the East Coast and worked at a NASA lab for about a decade near Washington, D.C., and then moved back here about 6 years ago and started working at Lawrence Livermore then. And this picture here just gives one glimpse of some of the work travel we do in our field. This is the coldest work trip I've ever been on. Got to minus 40 degrees up in Canada a couple days after this was taken. And this is, we went to a special facility in Saskatoon, Canada to measure some parts that would soon be integrated into our instrument and our satellite and are now in space today. And so you can see a typical team there, me and Natalie from the lab, colleagues from NASA Center, and universities. So with that, I will turn it to Natalie, and I will leave and come back in about 20 minutes.
Hi, I'm Natalie. I was born and raised in Germany. All the way through high school, I always liked to watch documentaries and go to public outreach talks like this. And they convinced me that I really wanted to do astronomy as my career. So I went to university to study physics. And then in 2010, I did an internship here at the lab, and I really liked the program that we were doing there. And so I've been coming back here for my studies during my schooling and my PhD. And I've been in the same group here ever since. On this picture, you can see again Megan and me, together with some of our colleagues from NASA centers and universities, at a similar facility that we had visited in Canada, but this one is the ALS in Berkeley, where you have a really beautiful view down from the hills over the bay. So the topics we are going to be talking about today is where are X-rays in the electromagnetic spectrum. And then we'll talk about a little bit in detail for why are astronomers actually interested in looking at the X-ray sky. You probably know the visible sky from just looking at the stars when you're camping. And then Megan is going to come back out here and show you how we design X-ray telescopes. And those actually have to go on satellites, and we fly them in space. And then specifically, Megan is going to show you how we built and launched a satellite called XRISM. And then towards the end, I'll be coming back and show you some exciting first results from the first year of observations with XRISM. So you may have seen the electromagnetic spectrum in school already. Basically, light is waves, and different light comes at different wavelengths. You're most familiar with the visible spectrum shown in the center of this graphic, because that's what your eyes see every day. But there's light at longer wavelengths and all the way to much shorter wavelengths. And so on the long wavelength side, you have radio waves. They don't carry a lot of energy, but you use those, for example, to listen to your car radio. If you go to slightly shorter wavelengths, you get microwaves that you can use to heat up your food. The infrared is the wavelength range just before the visible spectrum, where you use actually, that's the light that your remote uses if you wanted to switch the channel on your TV. The ultraviolet is coming a lot from the sun, and that's actually what's giving you your, that's what's actually giving you your sunburn. And then the X-rays, you will mostly see if you go to the doctors to get your teeth or your bones X-rayed. And towards that end of the electromagnetic spectrum, photons will actually carry a lot of energy. And then at the very far end, with really short wavelengths, you see gamma rays, which mostly come from radioactive decay. So mostly you don't encounter those in your everyday life. So why do we care about X-rays? First, for comparison, on the left-hand side, you can see an image of the visible sky taken with an observatory such like Hubble. And most of the dots here are actually galaxies, not stars. And so galaxies have a tendency to cluster together and appear in groups. They're not completely randomly distributed in the universe. But now if you look at the X-ray sky in basically the same region of the sky, you see an entirely different picture. The image on the right is a high-resolution image of that region in the sky, and you can see a large gas cloud that is between all of those galaxies that you can see in the visible spectrum. And the reason it's showing in the X-rays is because that gas is very hot, and hot gas emits X-rays. In fact, this gas is hotter than the surface of the sun. So now, Stan is going to show you that even though we are not able to see these wavelengths, we can still detect them and show that they're there.
We can just leave it on that for a second. Okay, so this first demonstration, so as you just heard, and this is probably something you're very familiar with, right? All of you have seen this before in school, but maybe you don't understand how important it really can be in science. And so we have over on the far left, we have long waves all the way over to the right where we have the short wave gamma rays. And just that middle spot, that very small spot in the center, is what we can actually see, right? So that's really important to understand. So what I want to do is provide you with a demonstration, because really today's talk about is how do you see these things that are on either side, the things that are really you can't see with your eyes. So I set up a little demonstration here, and we can go ahead and switch over to the camera. And this is something that you can actually do at home, okay? So what I have here is, yeah, you can see that. I have a little tiny solar panel that you can buy for about $3 online at Amazon, all right? And I have that connected with a wire lead over to a speaker. And by the way, this speaker's from Radio Shack. Does anyone remember Radio Shack? That was the original Makerspace stuff, right, guys? Right? I wish it'd come back. I think it's online, all right? So it's connected to the speaker. And what it's able to do is take whatever light hits the solar panel, and it converts it into electricity, which is sent to the speaker, and then you can hear it, okay? And so, unlike the things that you can't see, like X-rays and infrared, you can see visible light. And if I turn this on, Not a real pleasant sound, is it? But if I cover that, then it makes less of a sound, okay? But what about those things that you can't see? Is there a way that we can somehow detect those sounds? So we know that UV light is out there, right? All we got to do is sit out in the sun for a while, and all of a sudden we can detect it on our skin, right? Not a real pleasant detector. It'll turn red and sunburn, but that is a way that we know that UV is out there. We have other forms of light, like infrared light that is around us all the time, and we can also kind of detect that because when I point and click at my TV, I can do things like change the volume, turn the TV set on and off, and yet we don't see it once again. So this today is all about making that invisible visible. And so is there a way that I can detect that UV using a piece of technology? So I'm going to go ahead and use this solar panel, try to get away from some of that ambient light, and so you can hear it, right? Isn't that amazing? That's going on the whole time. Now, it probably sounds the same to everyone, right? Like changing the channel sounds the same as increasing the volume or turning the TV set on and off. Do you think it's the same? No, can't be, right? Can't be the same. So it must be some sort of code. And some of you are thinking, what kind of code is it? So I'm going to challenge you, students. Is there some way to take what I'm doing here and solving the mystery, decoding the code? Who thinks they can do that? Anyone? Look at those hands, all right? Head out to Radio Shack that doesn't exist anymore, buy these parts, get a channel changer, and see if you can't decode that binary code that's coming out, right? Very cool. Okay, so what we have today is we have these brilliant scientists with us this morning that have learned how to take a different form of light that you can't see, not infrared, but X-ray, and how they've been able to use all their knowledge and wisdom to be able to decode that information. And so by the end of today, maybe you have a few hints on how you can solve this mystery, okay? All right, thank you very much. And we're going to go ahead and continue.
Thank you, Stan. So now that Stan has shown you that we can actually detect all the lights from the different wavelengths, let's talk a little bit more in detail about what the X-rays can teach us if we observe them in the universe. And I already told you that hot gas emits X-rays, and so by looking at the spectra from these X-rays, we can actually learn about the dynamics and the composition of this hot gas. So to show you a few examples, again on the left you see an image of the Perseus galaxy cluster and the intercluster medium. And by the way of how galaxies cluster into groups and how the gas between those galaxies behaves, we can actually learn about the evolution of the universe. But then you have probably also heard of black holes. Black holes are super dense objects that do not emit any radiation by themselves, but by the way they interact with their environment, we can learn how they work. So in this illustration, this is not an actual observation, that's an illustration from an artist. You can see a black hole that is basically the end stage of a former star in a binary orbit with a supermassive star, and you can see that it is accumulating material from that star, and it's just absorbing all of that material. But also black holes exist in larger masses in the center of galaxies. And then another example, again with a actual observation, you can see a supernova remnant. You may have heard of supernovas, which is at the end of a life of a very massive star, it's going to explode and expel all of its material into the surrounding medium. And as it expels this gas and it's expanding, you see this shell that gets really hot. It's like really hot gas, and you can see that in these images. And these shells we call supernova remnants. So how do we learn about the composition and the dynamics? through spectroscopy. Just to go slightly back to something that you're familiar with is in the optical regime, with the visible light, if you have the white light and you shine it through a prism, light gets spread out, you see the different wavelengths. So on the right-hand side, you see the white light, on the left, you see a rainbow. All of you have encountered this before. And then if you actually count how many photons do you see at each of these wavelengths, that's what we call spectroscopy. And you can do the same thing, but with different technology at the higher energy, shorter wavelength X-rays. And so on the right-hand side here, you can see an example of such an X-ray spectrum. So basically on the horizontal axis, that's just the energy of the photons. And we cut that energy into very small bins, and then we count how many photons do we see in every bin. So on the y-axis, on the vertical axis, it just tells you how many photons did we observe in each of these very small energy bins. But now what you see in the spectrum, in the cyan spectrum, is that there's a lot of peaks and a lot of valleys where you don't see anything. And those peaks are actually emission from different ions. Each of these peaks is from a different charge state of sulfur. And if you have really high resolution in your spectrometer or your X-ray detector, you can actually see all of those individual features, and you can really learn exactly what's happening with the dynamics in the gas that you're observing. But if you have a lower resolution detector and you don't count the energies of your photons in as small of an energy bin, as you can see in the gray line, you'll have a much harder time to find out what is actually going on in the gas that you're observing. And so this is where the strength of XRISM comes in. For the first time, for certain objects, we are able to actually look at images at this high quality. Now, this spectrum that you see here specifically is actually taken at the Livermore lab with an apparatus on the ground where we can produce similar gases as the ones that we observe in space and learn exactly in a well-controlled environment which ions and which elements produce which parts of the spectrum, and then we can use that information to learn, just from looking at the objects in the sky, what is going on out there. Right. So what do we need to do to be able to observe X-rays? In this image, you can see just the Earth. It's on the ground, and then above it, the atmosphere. And these colored shaded regions show you how far the wavelengths of different, how far the photons of different wavelengths are actually penetrating through the atmosphere. So obviously, as you see in the middle, the visible light makes it all the way to the ground, which is actually why your eyes developed to see in that spectrum. You can also see that further on the left in the red shaded regions, that some of the radio wavelengths will also make it all the way to the ground. But then a lot of the infrared and most of the all of the X-rays and the gamma rays will be absorbed in such high areas at altitudes where not even planes or balloons are flying. So in order to build an X-ray telescope and be able to look at the X-ray sky, we actually have to fly our telescope on a satellite that's orbiting the Earth. And you can see some examples of those satellites depicted at the top. So then, what components need to go into our X-ray telescope? So the light would be coming from the right-hand side of that image, and we need to have mirrors, just as with optical telescopes, that collect a lot of light, because the objects that we're looking at are faint, and then that light gets focused onto the detector. Those are the basic building blocks that Megan in a second will tell you the details about. And then all of these are just stuck into a satellite and launched into orbit. So first up, we will talk about mirrors, but at first, we'll just have a comparison to the optical mirrors that you're all familiar with. So if you have an optical mirror and you look straight at it, like this little cat in the picture, the light gets reflected straight back at you. Those mirrors are typically made of a substrate of glass coated with a reflective coating of aluminum to show you that. And then basically how this works in more details and in more physics terms is you have the mirror depicted here as the yellow line, and then on the top of that is where you're standing. That's just material number 1, which has 1 refractive index. In this case, that would be the air. That's where you're standing. And then on the other side, like on the mirror material, you have another refractive index. In this case, that would be the aluminum coating. And so if you have light falling in at a steep angle A, it gets reflected at the same angle, right? And so if you look at it straight on, you'll get your image reflected right back at you. What doesn't happen in this scenario is refraction. So you don't get any light that goes through the mirror. And so now Stan will show you some experiments where you can see the reflection and the refraction in more detail, and then afterwards Megan will tell you how we do this in the X-rays.
Okay, thank you, Natalie. So once again, we're peeling away at the technology, getting closer to how do we see those X-rays, right? So we're going to rely on going back again to some basic science that most of you have covered already. Raise your hand if you've already learned in school about reflection and refraction, right? That's something we cover pretty early and pretty often. And it's really important to understanding that in order to understand how we see the X-rays. So I've got, again, another demonstration set up over here. And we're going to focus right now on this tank. It's a simple 2.5-gallon tank. And what I've done in this demonstration is provide us for an opportunity to see how light behaves as it passes through 3 different materials. The upper level is air. The second layer is vegetable oil. And the third layer is water. And I put a little bit of powder in there just so that you can see it. All right? Again, something you can do at home, a little messier than the other demo that I had, so be careful, that oil is really tough to clean. All right, so to demonstrate this, how light behaves, we can't use an X-ray up here, but I can use a laser. And so when I take a laser directly above and I point it down through, it just basically goes straight down through it, right? Pretty much what we expect, all right? So it goes through the air, it goes to the oil, and if it is changing in speed whatsoever, we really can't detect it because it's going straight down through. However, all I have to do, and this is a little trickier to see, so I'm going to try to do it carefully, is if I do come at a different angle, and I don't know if you can see the pointer, you can see that light has bent, right? It should be going straight along where that green is, but as soon as it hits the oil, it takes a pretty serious bend, and that's called refraction. And that's because the light changes from going through air, which is relatively easy, and then it hits the oil, and it slows down, and it starts to bend, okay? So that makes sense, right? But not only does the way that light behaves depend on the type of light that I'm using, you know, lasers or flashlight or X-rays, it also depends on the material that it's going through, and it also depends upon the angle at which the light is approaching, okay? And you saw that real traditional model that you saw throughout science, you know, the angle of incidence equals the angle of reflection. So we're going to do a little demonstration, and hopefully you'll get a good view of the angle as I send it through. So I'm going to change the angle from going straight down to coming in from the side. So there, now the light is not refracting, it is reflecting. And it is going down to the surface, lower surface of the oil, reflecting back to the upper surface of the oil, and then back down again. That's a very specific angle, we call a critical angle, and it results in a phenomenon we call total internal reflection. And it's the way that we send signals over a very long distance through things like fiber optic cable, all right? So what this demonstration is trying to show you is that so many things matter with light. The type of light matters, the material through which it's passing matters, or reflecting off matters, and the angle, right? The angle matters. So as we continue this journey to teach this audience all about how X-rays can be seen or detected, angles count, all right? And you'll see what we mean here in a second as we continue our talk. So we're going to go ahead and continue our talk with, I think it's Megan coming up.
All right, so this is perfectly set up. You guys learned that wavelength matter, angles matter. So now we're going to look back at this diagram, but think about it in the X-ray range, X-ray wavelength range. You have an incident ray that comes in again at angle A. We get no reflection. This is a big deal. We want to make X-ray mirrors. We're getting no reflection. What's happening? We're getting 100% refracted X-rays or absorbed X-rays. And this makes it very difficult to build an X-ray mirror. All right, so what do? We can play with the angle. So if we think about coming in at a very shallow angle now, maybe something even much shallower than is shown on the screen there, then we're able to get reflected X-rays. And this is what we call grazing incidence. So you can think of it as almost as like a rock skipping on a surface of water. And this is the basics of how we make X-ray mirrors for our telescopes. And this really drives what our telescopes look like. So we'll go back to this image you saw earlier of an X-ray mirror. So on the left, you see these shells. This is actually a cutaway. The shells in reality would be all the way, not quite circular or cylindrical, but close to it. So we have X-rays that come in from the left, these blue rays, and you notice that they're actually hitting those surfaces with grazing incidence with a very shallow angle. They hit there, they bounce, they hit again at grazing incidence, and then they get reflected to the detector. And so this is how we build X-ray mirrors with these very shallow grazing incidence angles. On the left, this diagram here shows us why we want to end up building very small reflectors, or very thin reflectors. You see in gray, if the reflectors are thick, some of the X-rays coming through get all the way through to the right, which is what we want, but others get absorbed by the side of the reflectors themselves. So we make the reflectors very thin. This minimizes the absorption, and we're able to collect as many X-rays as we want, or more X-rays, so that we can look at these very faint objects that are far away, and we can collect tons of photons and focus them down to our detector. So what does this look like? In reality, these are built from thin aluminum coated with gold. So you can see it in the image there, and Natalie is holding one up. And then because we want to collect many, many X-rays, we nest them. You saw the nested shells in the previous diagram, and here's an image of a quadrant of an X-ray mirror being built where you see many reflectors are being inserted there. This is partially built so that we can then collect a lot of X-rays. Okay, thanks, Natalie. And here's an image looking from the top at an almost completed mirror where you can see there are 4 of these quadrants put together. These orange lines are separating the different quadrants. And in this case, the X-rays would be coming from above and bouncing off these many reflector foils down to the detector. This is what a fully completed mirror looks like. It has actually more than 1,600 foils in here to make this mirror. And you can see around the outside, so in this case, the 4 quadrants are put together. There's some wires going to heaters to keep this at an even temperature when we're in space. And so some X-ray mirrors are built slightly differently, but this is a basic concept of how the X-ray mirrors are built. So now we need to talk about how do we detect the X-rays. So we'll move on to talking about detectors. At first, you saw the image of the Perseus galaxy cluster before, and this was made by kind of a standard workhorse digital camera that's sensitive to X-rays. And this is what's used to make nice images. It has millions of pixels, so you would have to zoom in very far on this image till you get down to individual pixels. And it's kind of similar to what you would have in your iPhone or a digital camera. It's just sensitive in the X-rays. But there's another type of detector, and one that I've worked on for many years, called an X-ray calorimeter detector. And this allows us to not just do imaging, but to do spectroscopy with the detector itself. And this cartoon shows the building blocks of a single calorimeter pixel. You have an absorber there that's going to absorb the X-ray photons coming in. You have a thermometer, a very sensitive thermometer, that will sense the change in temperature from that individual X-ray hitting the absorber. And then the heat flows from the absorber through the weak thermal link to the heat sink. And that kind of resets it so that it's ready for the next X-ray. So in time, you have the X-ray that hits. And then looking at the temperature as a function of time, you get this pulsed increase when the X-ray is absorbed, and then it falls back and resets to the base temperature. And what we do, our X-ray telescopes, we're not taking snapshots like, boom, it's done. We're usually staring at objects for hours, days, or even weeks. And so the whole time we would be staring at an object, we're counting photons and building up a spectrum, like what Natalie showed earlier, where you are counting the number of photons in a particular bin in your spectrum. So this is the building blocks of a single pixel. We can make this into arrays of pixels, which gives us both imaging and spectroscopy, although we're not at the stage yet of building millions of pixels. So here you see an image in the very center. That's a chip with 36 calorimeter pixels. There's wiring around it in this focal plane assembly. I'll show this movie as we zoom in on this calorimeter array. You can start to see the 36 pixels. And now we'll see an animation of X-rays coming in and hitting the individual pixels. And as the X-rays are getting absorbed, they're heating up different amounts depending on what energy of X-ray hit. So you can see the ones that are yellow are going to have been slightly bigger X-rays. The ones that were red were going to be slightly smaller X-rays. And so that's how we build up an X-ray spectrum with these calorimeters. So these are very powerful detectors for doing science, but there's a big challenge with them. And the big challenge is that they need to operate at very low temperatures. If we are going to sensitively detect the heat from a single individual X-ray photon, they need to operate at almost absolute zero. That's as cold as you can get from the laws of physics. On the right, you see, again, the calorimeter array there, and it sits at 50 millikelvin, 0.05 degrees above absolute zero. To keep it cold, what these instruments we build look like are big dewars. So the dewar, there's a diagram of that dewar on the left. It's large. You can maybe put your arms halfway around it. At the center, you have the detector that's very cold, and you have X-rays coming in from the top, from the X-ray mirror into the dewar to the detector. On the outside of this dewar, you're going to be at about room temperature, or in space, you'll be a little bit colder than that. And then you have nested shells. These are not the nested shells of the mirror, but shells that get you from room temperature to 130K, 25K, and down to 1 Kelvin. We use liquid helium to get us to about 1 Kelvin, and then an additional magnetic refrigerator to get the detector all the way down to 50 millikelvin. So this here is an image of what one of these instruments looks like. It's very far from something you can hold in your hand. So in the foreground there, you see some of my colleagues doing the final testing of this instrument before it goes onto the satellite. So that there, the dewar, the shiny silvery-looking dewar, is an instrument that is now in space. There's some components that aren't part of the instrument. The scaffolding isn't. Those like dryer hoses aren't. Those are just used for our ground testing. But everything else is basically the infrastructure so that we can get our detector cold. We then take an instrument like that, or that particular instrument, and we put it onto the satellite. So on the left is an image of the dewar with a detector in the center, and on the right is an image of the full satellite. So this is what it looks like. It's about the length of a short school bus. At the top, you have the X-ray mirror we discussed earlier. In this orientation, the X-rays would be coming in from the very top, from the ceiling, going through the X-ray mirror and being focused down into the dewar. One thing that catches people's eyes in this image is the gold color. You see it almost all over, that gold metallic. That is space blanket. So that's used on satellites to keep the thermal environment relatively stable when you're in orbit. This satellite's going to go into low Earth orbit, so a similar orbit to what the International Space Station is, where you're orbiting the Earth about every 90 minutes. And if you think about it, people think of space as cold, but sometimes it's cold. Sometimes you're in the dark and it's cold. Other times you have the sun beating down on you. So you can think about when the sun's beating down on you in California at the beach or just on blacktop, it gets very hot. And we don't want our satellite to be getting hot, cold, not just for the dewar. So the dewar has its own cooling system, but mechanical stuff inside there, electronics boxes just inside that whole area. So that's why you'll see satellites that often look like this with the gold foil. All right, and this, if you cut away the space blanket and the panels, you'll see something that looks like this. So again, at the top left, you have the mirror. So if you look at the blue part here, you have the mirror. You would have this would be pointed at the object you want to look at. You have X-rays that come down and are focused into the detector at the right. On this satellite, we actually have a second mirror. So the pink is also a mirror, a copy of the blue, and it focuses X-rays down to another camera that's more of the standard digital camera for imaging I talked about earlier. And that's to give us context when we're taking these very exquisite spectra, to give us context of what we're looking at. You see here also we have the solar panels extended. Those are extended shortly after launch. So we're talking in particular today about the XRISM mission, the X-ray imaging and spectroscopy mission. And at the heart of this is the detector array we talked about and the mirror we talked about. This is an international collaboration. It's led by JAXA, the Japanese Space Agency, with partnership with NASA and participation from ESA, the European Space Agency. So a lot of these missions are so expensive and complicated that you want to bring together the funding and the technologies from multiple countries to make this happen. This was developed from about 2017 to 2023. There was actually technology development for about 25 years before that, but for building this particular mission, it was these 6 years until launch. And part of the reason for that length is because we can't service this mission once it launches. We need to get it right. So every component is tested. You build your components into subsystems. Those are tested for their performance, for vibrations to withstand the vibration of launch. Then you put them into an instrument. You test that. You saw in a previous picture my colleagues up there. That was during months long of testing our instrument. And then you put it as a satellite. You go through the vibration, acoustic testing of the satellite as a whole satellite. And in our case, that happened near Tokyo at a JAXA lab just outside of Tokyo. And then the whole satellite goes on a barge down to the launch site, which is in an island in the southeast part of Japan. And so I'll show you a series of images, because since our telescopes need to go to space, there's a whole lot of work that happens when you're basically done with a satellite to get it up there. So this is an image of XRISM satellite hanging in midair, a very nerve-wracking time, after it's arrived at the launch site. And it first goes into this building. So you can see the satellite hanging there. And then the whole point here is to take the satellite and put it inside the fairing. The fairing you can see in both photos in white. And the idea of the fairing is it's going to protect the satellite during launch, and with the nose cone there, it'll make it more aerodynamic for launch as well. And then once you're through the atmosphere, it kind of falls away. It's a clamshell, and you get rid of it. So for this launches are expensive. So sometimes you launch multiple satellites at once. In this case, it was a dual launch. So on the right, there's part of the fairing, and there's actually a moon lander in there. A moon lander called SLIM that landed on the moon about a year ago. This is a Japanese moon lander. And then this series of photos we're showing putting XRISM on top of that. After that's done, you would put the fairing and the nose cone on the left on top of it. Then once this is inside the fairing, we put the whole thing on top of the rocket. And this is an image of the completed rocket. This happens inside a vehicle assembly building at Tanegashima Space Center. That's a 25-story building. You can see our satellite inside the fairing at the very top, so you know that was the size of a school bus. So this is very tall. When it's being integrated on top of the rocket motor, this is a 2-stage H-2A Japanese launch vehicle. You feel like it's being integrated into the building, and scaffolding inside the building. But really, the scaffolding itself is mobile. It's being integrated on top of a mobile launcher that's going to roll this thing down to the launch pad. At the bottom, these are the vehicles that are going to roll it. They have 56 wheels each, so 14 rows of wheels, because this is very heavy, so you want to spread the load across all of these wheels. And then it rolls about a half mile. It's pretty slow, not too slow, but pretty slow. That takes about a half hour to go about a half mile. And here's an image of it at the launch pad. You can see people on the bottom of these images for scale. One thing to note here are these lightning towers. Now, I've told you the years it takes to make these, the expense. You have a whole team of meteorologists monitoring the weather. So you never would roll open this sliding door on the building, which is, by the way, the largest sliding door in the world. You would never roll that open if you know there was going to be lightning. You would never roll the launch pad if you thought there'd be lightning. But you don't want to take the chance. So if you get all the way out there and something happens, you want to make sure the lightning hits something that can just disperse it and not ruin the satellite. And you even have little lightning rods on the mobile launcher itself in case something happens in that half hour before you get out there. All right, so this is the launch picture, the long-awaited launch on September 7th, 2023. On the left, you can see an image of the launch pads. There's actually 2 launch pads there that are used. People call it the most beautiful launch site in the world with that beautiful blue tropical water. And we have this two-stage rocket to get us into low Earth orbit. And this is an image. Of course, we can't actually take a picture of the satellite once we're up there, so this is an artist's conception of what XRISM would look like with its solar panels deployed in orbit. And so that's where it is now, over us, coming around the Earth every 90 minutes. And so for about the last year, a little more than last year, we've been up there taking observations. And now for the last section, I'll hand it back to Natalie to talk about some of the science we've been doing with XRISM.
Thank you, Megan. Okay, so what you can see here is the press release for what we call the first light observation. For every satellite that we launch into space, there's usually a first object that we observe as a science case, and typically an object is chosen that really demonstrates the capabilities of the satellite, and then it's shown to the world that the satellite is working really well. And then everybody else can ask for time to actually look at the objects that they want to study. So in this case, the first light observation was a supernova remnant. Remember, the shell of the gas that the supernova expels into the surrounding medium. And this is actually the same supernova remnant you have seen earlier. So in the background there, you see the image as taken with the imager on XRISM. It's a little bit more pixelated because the earlier image that we looked at was taken with a satellite whose mirror was specialized to take really high spatial resolution images. But for XRISM, we use slightly lower spatial resolution. And then in the foreground, you can see the spectrum that the colorimeter has taken. And we'll look at that spectrum in a little bit more detail. So you can see all these little peaks that are coming out. And all of these peaks, like the earlier lab spectrum that we had looked at, belong to different elements and different ions of that element. So on the left-hand side, you can see mostly lighter material like silicon, sulfur, and argon, and you can see that those peaks are really sharp. And those are narrow emission lines, and they correspond to a gas that is 10 million degrees hot. And that 10 million degree hot gas primarily comes from that shock region at the edge of the supernova remnant, where you can see indicated in the image in red, where the material hits the surrounding matter. But then if you look at the right-hand side, you see an iron line that is really broad. And that iron line belongs to gas that is 10 billion degrees hot. And that 10 billion degrees gas is coming more from the center of the supernova remnant, indicated with the yellow circle. And those are parts of the ejecta, like from the atmosphere that is getting expelled. And so for the first time with XRISM, we can actually see a spectrum of a supernova remnant in this high resolution and learn more about the morphology and how these supernova remnants act, behave, and are composed. So for the next example for a source that we observed is a stellar mass black hole. As I mentioned earlier, black holes come in different sizes. Stellar mass black holes are born from a dying star that went supernova. Typically, in order to be able to observe them, they need to interact with an environment, and for the most part, they will do that if they're in a binary system. So a star system that originally consisted out of 2 stars, and now it's 1 star and the black hole. And again, you see an artist conception, in this case of Cygnus X3. That's the 3rd brightest X-ray source in the stellar constellation Cygnus. And as you can see, it consists of a massive star here in the center, and these massive stars tend to have really strong stellar winds. It's a little bit like a solar flare, but it's just a constant wind that's coming off of that radiation, and you can see that depicted as these little stripes. And then this little tiny black dot that you see on the right is the actual black hole, and as that black hole wanders through the stellar wind, it starts accreting material. That's basically material falling onto the surface of the black hole. And as it does that, it actually has to a little bit spiral down onto the surface, and it builds this accretion disk that you can see as that yellow disk there. And then some of the material is actually also launched away at high speeds, which you can see as these jets. So if we look at the broadband spectrum that XRISM has observed, you can see again on the left-hand side narrow emission features from the lighter elements like silicon and sulfur, but we want to focus for now on the iron region on the right-hand side, where you can see there's something much more interesting going on. And so if we zoom into that iron spectrum, you can see that there are actually some valleys in there. We call those absorption lines. That is when light disappears from the spectrum. It's just there's photons missing in these areas. And then you see the peaks, which are the emission lines that you are familiar already from supernova remnants now. And you can see that for each of these valleys and peaks are from different ions of iron. And by studying really carefully the strength and the width and the location of these lines, we can learn actually what these binary systems look like because these, like the reason I'm only showing you artists' illustrations of these is because they're too far away and we do not have the spatial resolution to actually observe those. We cannot visibly tell these apart. It's just light coming from that system. And so in this case, the absorption lines actually tell us that that is from material coming from the larger environment of the system, mostly from the stellar wind, while the emission lines are from hot gas that is closer to the black hole. But then I also told you that black holes exist in larger scales. What you can see here is an optical image of a galaxy. It's another galaxy far away. And at the center of each galaxy in the universe, there's what we call a supermassive black hole. Unlike the stellar mass black holes that have the mass of a few times to a few 10 times the mass of our sun, these have the mass of 10 million to 10 billion times the mass of our own sun. And these live at the center of every galaxy. Some of them are quiet and we can't observe them, but some of them are actually absorbing material and then therefore shine bright in the X-rays, and in that case we call them an active galactic nucleus. So here you can see the depiction. That's again an artist's illustration because we cannot resolve these images by just looking at them. We don't have mirrors that have that kind of magnification that we can see that in detail. But in principle, these active galactic nuclei, they again consist of a black hole, which in this case you can see as the black dot in the middle. They have an accretion disk where matter is spiraling towards them to fall onto the black hole. Again, that's the blue regions here. But they also have a roughly donut-shaped cloud gas ring, which we call the torus. That's further out, and also they have jets of material that are ejected. What you can also see in this depiction is that there is radiation, X-rays actually, coming from the base of the jets, and that irradiates different parts of the accretion disk and the torus. And as these X-rays interact with the gas from the accretion disk and the torus, partially it gets reflected, partially it just gets absorbed and re-emitted, and those X-rays we can observe with the satellite. In this case, you can see XRISM looking at it. I should note that this cartoon is not to scale. So XRISM is far, far away from this AGN. And then also the vertical extent of the torus and the accretion disk relative to the jet here are not to scale. So now if we look at the spectrum that we saw from XRISM, you can see the different components actually behaving differently. So the blue line that you can see in that spectrum is from the accretion disk. It's really washed out. It is moving the X-rays that are reflected to a lot of different energies. But you can also see it depicted in the orange band that there is an actual distinct iron line. So a broader iron line coming from what's called the broad line region, which is the edge in yellow up there in the cartoon. That's just before the torus. You can see that that makes a really broad iron line. But then on top of that, there's also a really narrow iron line that really peaks, and that's shown here with the pink model, and that's coming from the torus. And so with XRISM, for the first time, we can actually, in the spectrum, distinguish all of these individual components. Before that, it was just like one wide iron line, and we did not have the spectral resolution to look at these. So as you can see, XRISM is actually like really teaching us new things now that we have it in space. So what have we discussed today? We learned where the X-rays fall onto the electromagnetic spectrum. We also discussed why astronomers are interested in observing the X-rays, the universe in the X-rays, and we learned that in comparison to the visible sky, you can see really a lot of different features, and you learn much more if you look at the sky in all the different wavelength bands. Megan explained to you how we design our X-ray observatories, how we integrate them into satellites and launch them into space, and told you what the mission goals are for XRISM specifically. And then we showed you some exciting first results from the first year of observations with XRISM. So thank you very much.